The next part of chapter 16 is specifically about the pH scale and pH calculations. So pH in French basically means the power of hydrogen. So pH basically evaluates the relationship between the hydronium, which has the extra H in it, and the hydroxide from the base relationship. So the normal pH scale ranges from 0 to 14, and it is color-coded, a rainbow. So neutral solution, meaning that the hydronium and hydroxide contents are equal, is a pH of 7. Acidic solutions have a pH of anywhere from 0 to 7. And then basic solutions have a pH of 7 or above, up to 14. So just some general examples you're probably familiar with. So battery acid and stomach acid are very acidic, very low on the pH scale. Vinegar, orange juice, tomato juice, mid-acidic on the pH scale. Black coffee and urine, still acidic but higher up on the pH scale. Water is generally neutral. Seawater is slightly basic because of the salt. And then you get into your bases. So baking soda, any type of salt is a base. And then you've got indigestion tablets like Alka-Seltzer or milk of magnesia. Ammonia cleaning solutions are basic. Soapy water, specifically soap. And then bleach and specifically drain cleaner are the higher, more alkaline substances. So pH calculations. How do you calculate pH? Well, it's an logarithm. Don't be scared by that. So pH equals the negative log of the hydroxide concentration. So you're going to be using the negative button on your calculator and the log button. When you hit the log button, it's going to give you a parenthesis. You type in the number after that parenthesis for the hydronium ion concentration, and then you have to end parenthesis before hitting equal. It's going to give you an error sign. So basically, pH is equal to the negative of the common logarithm of the hydronium ion concentration, or more simply put, negative log of the hydronium ion concentration. So let's do some examples. So example 1, what is the pH of a solution if the hydronium ion concentration is 3.4 times 10 to the negative 5 molar? So we're just going to use this equation. So pH ion concentration, which is very specifically given to us. Okay, so you would hit negative button, log, and then enter that number. The pH is going to be equal to 4.47, 2 decimal places. Simple as that. This is the most basic example because it's telling you the hydronium ion concentration very clearly. Okay, what about an example that doesn't specifically tell you the hydronium ion concentration? So find the pH of a 6.02 times 10 to the negative 6 molar hydrochloric acid solution. Well, this is where you need to go back to the beginning of the chapter. We said if you know the solution is an acid or a base, in this case an acid, if it's an acid, the molarity is equivalent to the hydronium ion concentration. So in this case, because this is an acid, this value is the hydronium ion concentration. It doesn't specifically say that, but you know that because of the acidic solution. So once again, you just plug your number into the equation for pH. And you're going to round to 2 decimals. So in this case, pH equals 5.22. And if you look at this value, 5.22, and you look at the substance, which is acidic, that doesn't make sense because acids have a pH lower than 7. Okay, what about this one? Find the pH of a 3.06 times 10 to the negative 4 molar HNO3 solution. Well, is HNO3 an acid or a base? It's an acid, nitric acid. So once again, this is telling you the value of the hydronium ion concentration. So go ahead, pause the video, see if you can set this one up and solve it. All right, so pH equals the negative log of 3.06 times 10 to the negative 4. Hopefully you solved that out. Rounding to 2 decimals, pH is equal to 3.51. Once again, we have an acid solution. We have a pH less than 7. It makes sense. Just another way to verify your answer. Okay, but what happens if the substance in the question is a base? So sodium hydroxide is a base. This value is no longer the hydronium ion concentration, but it's the hydroxide ion concentration. But for this equation, we need the hydronium. This requires a little bit more work. So go back to the beginning of the chapter. We said the Kw, which we know the value of, is equivalent to the hydronium ion concentration multiplied by the hydroxide ion concentration. So in this case, we know Kw, and we know OH because we have a base. We do not know H3O plus concentration. So we're going to have to solve for it. Okay, so we're solving for the hydronium ion concentration. So we're going to divide both sides by the hydroxide ion concentration. So dividing those two, and remember, it really depends on how you're putting in your calculator if you get the right answer. Our hydronium ion concentration is equivalent to 1 times 10 to the negative 11. So now we finally know the hydronium ion concentration. You couldn't just use this in this equation. That's not the hydronium ion concentration because we're dealing with a base. So now that we finally know the hydronium ion concentration, now we can use this example. So if you're given an acid, you just use that number, plain and simple. If you're given a base, you have to first follow these steps to find the hydronium ion concentration. So now we can say that pH equals negative log 1 times 10 to the negative 11. Plug that in your calculator. I get a pH of about 11. Does that make sense? Well, we have a base. Bases have a pH of above 7, so yes, this does make sense. Okay? If you did it the other way, your number wouldn't make sense. So always remember, if you have an acid, the value given to you, you just plug into the equation. If you have a base, the value given to you is the hydroxide concentration. You have to solve for the hydronium ion concentration. So we can also calculate the poH. poH is the negative log of the hydroxide ion concentration. So find the poH if the hydroxide ion concentration is 1 times 10 to the negative 7. Well, in this case, it's being very clear and it's telling you what the hydroxide ion concentration is. So you can just plug this value into your equation. And there are no units for pH or poH. So plug that into your calculator, and you would find that the poH is equal to 7. And we'll figure out how pH and poH relate in a couple minutes. Or maybe the next video, I'm not sure. Okay, so now find the poH of a 4.5 times 10 to the negative 3 molar calcium hydroxide solution. This is the exact same thing we just did, except now we're talking about bases. So this is a base. This value is equivalent the hydroxide ion concentration. So once again, we can just plug it right in because it's a base that is the hydroxide ion concentration, and that's what's needed for poH. You can just plug it right into the equation. So try that out, solve it, see what you get, check with me. Okay, so solving this, I got a poH of 2.35, no unit. And remember, this is not poH. Okay, this is not pH. So you're not looking at that pH scale. We're now solving for poH. Okay, try another one. Find the poH of a 3.06 times 10 to the negative 4 molar HNO3 solution. This is going to require more work. In our previous example, we had a base. Because it was a base, this was the hydroxide ion concentration value. Now, we have an acid. So it's still important that you remember how to identify the difference between an acid and a base. Acids start with H's, bases end in OH. So now, this value is not the OH concentration. It's the hydronium ion concentration. So once again, we will have to use this equation to solve for what we actually need for the poH equation. So we know Kw is always 1 times 10 to the negative 14th. And in this case, we know the hydronium ion concentration because we're dealing with an acid. And the molarity is equivalent to the hydronium ion concentration for an acid. We do not know the hydroxide ion concentration. Okay, so pause the video, try to solve this out, see if you can get it. All right, so I'm going to divide both sides by my hydronium ion concentration. The goal is to get the hydroxide ion concentration. So this step is similar to what you did, or is what you did in the previous video when you were solving for H3 or plus or OH minus concentrations. So now I can say that the hydroxide ion concentration is equivalent to 3.27 times 10 to the negative 11. This is also important that this is also the importance of why you need to know hydroxide versus hydronium. I'm not saying OH minus and H3 or plus, I'm saying the actual name. Okay, so now that we know this, now we can use this equation. So poH equals negative log of the hydroxide ion concentration. So go ahead and solve that if you haven't already. You should get poH is equivalent to 10.49 or 10.5, depending on how you round it. Okay, so how do these actually relate to each other? So this is kind of foreshadowing into the next video. So when you're looking at a solution, the pH and the poH are related. If you add them together, pH plus poH should equal 14. Okay, so if you look at these charts, just some examples for you, you can see the concentration of hydronium versus hydroxide, and then you can see the pH versus the poH. So for something that has a very high hydronium ion concentration, it has a very low pH. It's very acidic. If you look at something that has a very high hydroxide ion concentration, it's going to have a very low hydronium. Because of that, it's going to have a very high pH and be very basic. So pH plus poH should always equal 14. That's another way, just one more way you can check your work. So I'm going to kind of foreshadow here. I'm actually going to go back and do these again in the future. So find the poH given an acidic solution with a pH of 4.5. Well, before, I didn't know the pH to find poH. I only knew a concentration. Now, I can use the formula I just showed you. So now I can just use this equation. So I know my pH is 4.5, and finding my poH, this should equal 14. So obviously this is pretty simple math, it's just subtraction. So 14 minus 4.5 means my poH would be 9.5. I have a low pH because it's an acid and a higher poH. That's what you will have for an acidic solution. So once again, just another way to verify. Okay, let's complicate things slightly. Find the pH given a base, calcium hydroxide, with a molarity of 4.5 times 10 to the negative 3. Well, if this is a base, this value is not pH or poH, this is hydroxide. Okay? I don't really have to use the Kw equation to get my hydronium to get pH. Instead, I can use this equation to find pH, because I can first find poH using this equation. Okay, so I'm going to do this first. I'm going to use the negative log of the OH minus concentration to find poH. Plug that into your calculator. Negative log of 4.5 times 10 to the negative 3. You get a poH of 2.35. Okay, then I can use this equation to find pH. So I know poH I just solved for. I know what the equivalent of the two has to be. So now I'm just going to subtract 14 minus 2.35. You can never have a negative number for pH or poH. My pH is going to equal 11.65. Does that make sense for a basic solution? Yes, it does. Bases are above pH. Okay, so finding pH and poH, you're going to use either problems, the negative log of the hydronium to find pH, the negative log of the hydroxide for poH. But if you already know one or the other, you can simply use poH plus pH equals 14. There's many different methods for solving problems in this chapter. It doesn't matter which method you use as long as the instructions in the worksheet or test question don't specifically tell you to use a various method. So always just make sure you're checking what's being asked of you and in what method when you move on.